Good morning, mathematicians. What are we gonna do today? I got no idea. Maybe some math. And, maybe some math. And, maybe some math. And I don't know what else. That's about it. Probably just some math. I got no idea. Do you ever wonder why I am the way that I am? I sure don't. Uninteresting question. What is interesting is whatever is happening on arXiv today. Hello, Matthias. Hello, Simon. Presumably that's how I say Simon. Hope everyone's doing well. Yeah. Let's go over to arXiv. Let's go to arXiv. This is always a good excuse for me to be checking. You should be checking subjects that you're interested in daily to see what's happening. I don't think there's anything new here in the last couple days. Let's see. You can see my saved searches, the things I tend to check. Good morning, quality content. On the one algebra of double cosets for a general linear group over a finite field. Interesting. Yeah. arXiv has so much stuff daily, it's hard to keep on top of it. Yes. But it doesn't become easier if you don't check it. So you should definitely be seeing what's happening. Ooh, what's going on here? You should definitely be checking what's happening daily. Ginsburg, you absolute goat. You're still publishing crazy stuff. It has been known for a long time that X between IC sheaves may often be expressed in terms of HOMs between cohomology groups. Okay. We prove a more general result under weaker assumptions. The result used to describe the action of derived satake on a Schriek peer objects and show the equivalence enjoys a new kind of functoriality with respect to morphisms of reductive groups. Huh. Okay. Very interesting. You've subbed to the subjects of interest after 2 days, couldn't keep up. Yeah, I did used to be subbed to the emails. I don't like that. Good morning, Ken. Ken, I hope you saw the short that I made, which finally answers your question. Yeah, it is easier to not check it. Yeah. But yeah, if it's still a good idea to just go there, check it up, check it out on your own every few days. We use the yoga of weights, given a connected algebraic group, G variety, equivariant derived category, have the stacky quotient, stratification, something pure, embedding geometrically constant. Okay. Whew. There's a lot going on here. Okay, theorem 1.1.1. If these conditions hold, then there's an isomorphism here. I see. Interesting. This is just for the case of the torus action. The geometers have fooled us long enough. Yeah. Fool me once, Shame on analysis. Fool me twice. Shame on the geometers. I don't know. Watch a short. It was awesome. But is there a problem where the order of G is supercomposed number so that we use every single trick to figure out as much as we can from the group? Yeah, I mean, I'll probably make some other shorts going over common CeeLo problems. There's a couple other ones that would be nice to do that highlight some common techniques. Like there's another technique where you use that I saw from a note of Keith Conrad that seemed really nice. And yeah, just a couple other common problems. But you know, I'm not a group theorist, so I don't know what the process is. I mean, in general, life is hard. Group theory is hard. So whenever you start to read about motives, it starts sounding like Buddhist philosophy. Well, maybe it is. Maybe it's all connected, man. Hot is basically hit. You don't know any other exercise puns. Yeah. How do you know when you're working on... well, that's the neat part, Dason. You don't. Let zeta be a primitive 24th root of unity. Let zeta be a primitive 24th root of unity. You know what? And let's even... That's zeta, by the way. I don't know if you can tell, but that's zeta. E 2 pi I over 24. I'm gonna pick even. I'm not gonna let it be I'm gonna pick one, and you can't stop me. For what square-free integers does the square root of D lie in the field extension zeta? That's a nice question. That is a nice question. Well, don't we always have, like, how does it go? So, like, zeta plus zeta bar should be real, right? I think, if I'm remembering, this is always a real quadratic extension. Is that true? Oh, I think so. Although maybe I'm confusing with when we have if we're joining a pth root of unity, I guess life is easier. Okay, but I guess we have the pth roots of unity, right? Like if we have a 24th root of unity, then we should have the 2, 3 times 3. Right? So we should definitely have, and then, yeah, I don't know if I'm remembering. Yeah, what are the roots that we get? Can we always predict those roots? Oh, but I guess, yeah, specifically we want square-free integers D that lie in the extension. Yeah. Okay, well, let's think about the degree of this extension. It should be... I guess it will be... We've got to think, because we want to, like, break this down as, like, a composite of extensions. So it should be something like, because I think we have separate formulas for like prime powers. The degree is 524. Oh, right. Yeah. And 524 is What's the formula? It's like, what is it? It's like if the factorization is like this, then it's what? P to the n minus 1 times p minus 1? Is that right? Phi 24. Nope, that's not what I meant. I can't believe I clicked on a Stack Exchange post for this. What am I looking at? Let me just go to Toshin function. Oh yeah, here we go. Phi pk. Nice, I was right. I was right. Good morning, Russ. Yeah. So, right. So this is 2 squared times 2? Right? 2 to the power of 2 times c minus 1. 3 to the power of 0 times 3 minus 1. So that's 8, right? Yeah, so this is a degree 8 extension. Well, I guess the thing that we could do is also look at the Galois group and figure out, based on the Galois group, how many degree 2 extensions there are. So is it just I always get I'm used to thinking about just a prime case, so I don't remember what generalizes, but Galois group of 24th roots of unity. This is just the multiplicative group of Z mod 24. Is that always true? Yeah, okay, this says that is true. Which an abelian group of order 8. Well, that's what AI is, but I'm willing to trust it for now. So yeah, multiplicative group of order multiplicative group of Z24, which how do we break that down into what should that be isomorphic to? This group of units. So yeah, how does this decompose? How does the unit group decompose? Is it just isomorphic to? Is this preserved? Am I crazy for thinking that this is preserved? Euler's totient counts exactly the invertible elements, right? Yeah, but I need now I want to know the exact group structure. So does it respect the sum in this sense? Because, right, Z24 will split as this. Am I a member of the P.A.D.X? Nerdy Quagsire, you know the answer to this question. Which, by the way, I was looking into finally making some merch, gang. So, but I just don't know what a good website is, because I could buy a bulk amount of t-shirt. Like I could buy a bulk of shirts and then handle distribution myself, but that's a lot of work. So I was trying to find, I don't know, I made a post on Reddit in some YouTubers thread, but no one had answers for me. Well, I posted in NewTubers. I guess I'm not a new tuber. Definitely have a cyclic subgroup of order 8 and then use the fundamental theorem. Yeah, do we have a cyclic subgroup of order 8? Is that true? I think we do. I mean, I'm pretty sure this argument should work, right? So this should be well, no, this wouldn't be a cyclic subgroup of order 8, because yeah, I suspect that this is true. And then if I'm right about that, if I'm right that it respects this decomposition, then maybe, yeah, let's double check here. Multiplicative group of units of Z mod 24. Taking units defines a functor from commutative rings to abelian groups, and that's some adjoint. Yeah, okay. So yeah, it should preserve the sums, right? For prime P, powers of 2. Okay, here's one that we want. Okay, so the group of units of a power of 2 will be that. Okay, great. So this will be isomorphic to Z mod 2 cross, let's see, what did it say? K minus 2. So this should be Z mod 2 cross Z mod 2, and then cross Z mod 2. So I think that's right. This is this one, and this is here. Great. Okay, so we're off to a good start. Is this even the best way? I don't know. Okay, great. So we've got a bunch of Z mod 2s. Now what? So I want to know what are all my subgroups of order 2. And I think they're just, I think we basically have like three subgroups of order 2, right? So A1, A2, A3, I'll call them. And these are, I don't know, maybe I should call them H because they're subgroups. I don't know. Right, so that'll be like H1, H2, H3, where we have the non-trivial Z mod 2 factor in either the first, second, or third position. Is that all? Because what if I looked at the subgroup that was generated by this element? Yeah, that's also, or sorry, by this element, 0, 1, 1. Oh yeah, wait, we want the index to be 2. Right. That's true. We want the index to be 2. Right. So we want the sub-extension. So Q adjoins zeta over E. We want this to be 2. And that is the order of the full Galois group divided by the order of the sub-extension. No, wait. I have things backwards. We want this to be order 2. And that is the full Galois group. Divided by the Galois group, the subgroup here. Yes, okay, that makes more sense. Right, so we actually want to find subgroups of order 4. So what do our subgroups of order 4 look like? So let's say H12, H23, and H13. So by this I mean like H13 will be like Z mod 2 cross the trivial group cross Z mod 2. So we definitely have those 3 subgroups of order 4. Is there any other possibility? Yeah, I guess then we also have Z mod 2 cross. Is this really the best approach? Somehow I feel like this can't be the best approach. Yeah, there's got to be a better way to solve this problem, actually. Because I'm looking at all quadratic extensions, but this is... no, well... I don't know. Isn't the Galois theoretic proof of quadratic reciprocity exactly checking when square root p is contained in zeta or something like that? Maybe. Yeah, this is not the best way to do things. Because I mean, if we do it this way, we're gonna end up getting 6 groups. And then what? Yeah, because if we were to see this approach out to the end, then like what would be next? Well, we would write down the actual automorphisms that correspond to all of these things, and then try to compute the fixed field. I mean, we know that we have a basis in terms of powers of zeta, right? Well, I guess, yeah. We could take a basis in terms of powers of zeta. Yeah. Well, I think it's clear how to do it, Ken. You basically just take like a linear combination like this, and you want to know everything that's like pointwise fixed. So you take your phi and apply it, and then you should be able to describe how phi permutes the zetas, because it's just gonna multiply like their exponents, and then you get some rearrangement of these, call it zeta n1, n2, blah blah blah, and then is basically just linear algebra from there. But then I guess you'd need like what to somehow constructively apply the primitive element theorem to determine your quadratic. It should be doable, but yeah, this is definitely not the most viable approach. Okay, so let's rethink this. Yeah, I don't know what's the best way. Let's go over. Let's get some inspiration here. Let's look at God, what's the name of these extensions? The cyclotomic extensions. Cyclotomic extension. Maybe we should be looking at some Keith Conrad notes. I don't full on want the answer, but I do want to see what are some useful facts that I'm forgetting here. Yeah, could we somehow use something about the primes that ramify somehow? Bad memories of Galois theory exams. How could you possibly have a bad memory of a Galois theory exam? This is inconceivable to me. Okay, this isn't useful. Let's see. What can we get from here? The square free requirement does bring to mind quadratic extension stuff. Yeah. Yeah, but I think that's just, well, I don't know. Yeah, Keith Conrad, exactly. Exactly, G. Mozzie. You're bang on with that one. Total snooze fest, to be honest. Mildly hot take. We should replace Galois theory with homological algebra or categories as a mandatory algebra course. That is a pretty hot take. I mean, but I don't think it's entirely wrong. I mean, Galois theory is amazing and beautiful. But yeah, arguably homological algebra and category theory is of wider application to more algebraicists. Yeah. So I still like Galois theory though. Let's see. I wonder if there's general stuff. I'm kind of tempted now to actually look up general stuff about quadratic sub-extensions of cyclotomic fields. Let's see. Yeah. Yeah, this is always, yeah. Oh, not its, well, its conjugate is its inverse. So I was right about that. Each pair of relatively prime integers. Oh, right. Yeah, because, so I think the answer is only one. Because I think there's only ever one totally real quadratic extension. So I think all of the other quadratic extensions are complex. Am I in the final year of my PhD? I sure hope so. I sure hope so. Almost certainly yes. No, certainly yes. Certainly yes. Yeah. No, now that I'm seeing this, I'm pretty sure that there's a theorem that says there's a unique, totally real quadratic extension. I'm pretty sure. Yaman, are we both graduating together? Incredible. Yeah, so it should just be one. It should just be one integer. When am I graduating? I don't know yet. I could maybe defend my thesis this fall, but maybe it makes more sense to just stay on for the winter to get TA ships. Yeah, but I guess the question is we still need to determine that integer. So let's look at this example. Actually, I should go soon. The 901. I need to do some work. Show that for each pair of relatively prime integers, both at least 3. Okay, so that's kind of an issue for this case of 2, but he does have the example of 12 there. Wait a second. M equals 4, M equals 3. Ah, yes, I see. Okay, great. So this should work for our example. Okay. 24-hour office stream when I pass the defense? Maybe, except I'll be sleeping for a good deal of that 24-hour thing because I'm not going to let anything get in the way of having a good sleep. What's a criminally underrated field of study in math? I think everything's rated appropriately. That's my hot take. Hi, can I prove that if this pair has the homotopy extension property? No. I cannot. Not off the top of my head right now. It's been way too long since I've done any serious homotopy stuff like that. And A is contractible, then X is homotopy equivalent. Oh, okay. Maybe I could? No, I can't even write down the homotopy extension property from memory. Just diagram chasing, but you don't get the intuition. Well, the intuition kind of makes sense, right? I mean, if it has the homotopy extension property, then somehow from A to X, then somehow all the interesting homotopy information is contained in A, right? Everything can be extended. Jose, I was hoping you'd show up to save the day. If the Galois group is that, then you have 7 quadratic extensions. Yes, but what about? But the original question was about the quadratic extensions that was the root of a square-free integer, and so I think the other quadratic extensions will be complex. Like, am I wrong in thinking that we should have a unique, totally real quadratic, quadratic extension? Is that crazy? Like maybe I'm being crazy there. But I think that might be the key to the result. I don't know. Yeah. Okay. I may or may not revisit Edit Smith the homotopy question tomorrow, but yeah, because it's end time for the stream. You took Galois theory and an introduction to representation theory last semester. That is a great combo. Preferred rep theory, way more until you learned about algebraic functions and Galois theory in other fields like topology. Yeah. Well, just wait until you do learn about the Artin conjecture. Representations of Galois groups. That's a beautiful, harmonious place where it all comes together. Get your life back on track. Learn homotopy theory. Yeah. You'd say that complex analysis in multiple variables is most criminally underrated? Really underrated? I don't know. I feel like complex analysis, well, maybe not in multiple variables, but I don't know. I feel like that's a pretty popular thing that people agree is cool and good. Yeah. We have square root 2 and square root 3 in this example. Okay, so I was wrong. But maybe, is it true for the Keith cyclotomic field? Is it true that has a unique real quadratic extension? The relation between topology and homotopy theory is purely incidental? Oh, I don't know about that. Homotopy theory is just an extremely special case of topology for people who are too weak-minded to conceive of non-Hausdorff spaces. There, I said it. Everyone was thinking it, but I'm the one that said it. You heard it here first, folks. Because the group is cyclic in the prime case. Because the group is cyclic in the prime case. Wait, is that true? In prime case? Wait, is that true? I don't think that's true. Is it true? In the prime case? Okay, wait. Let's find a prime. Yeah, what about Z mod 7? What about Z mod 7, right? This is isn't it isomorphic to this? Am I crazy? It is cyclic. Okay. Yeah, I guess I'm losing my damn mind. Non-Hausdorff is usually excluded from differential geometry too. Yeah, because they're weak. They can't handle it. It's too hard for them. I said it. That's what I said. Everyone's mad. But you're only mad because you know how true it is. Totally different from single variable case. For instance, holomorphic functions in multiple variables can't have poles? What? Multiple variables can't have poles? Interesting. Oh, it is isomorphic to Z mod 6. That's true. Huh. New wave infantry. The X is not a variable. This means the multiplicative. This means the multiplicative group of this. Yeah. Still have poles along divisors, just a different notion of pole. Yeah, that makes sense to me. Okay. Well, maybe we'll finish this. Maybe we'll finish this tomorrow. Maybe I'll chat with Jose in the office later about how to actually solve this problem. And we'll talk more about it. Yeah. I'll see y'all then. Kay needs to go back to the basics. Langland's time. Yeah. Langland's time. Yeah. Okay. I'll see y'all